In the first part of this practical exercise, you're going to be making some measurements of voltage from a battery as a function of current delivered by the battery. And you will be fitting it to a model that says the output voltage of the battery is equal to minus Rs, the source resistance, times the current drawn by the battery plus V0, which is what's known as the open circuit voltage of the battery, or the voltage of the battery when it's delivering no current. Now what you will find is that you'll be fitting this, comparing it to y equals mx plus b. And what you will find is if you draw a graph which has the voltage going all the way down to zero, perhaps if we had a graph like this and we plotted voltage up the y-axis versus current along the x-axis, and you'll have currents going out to maybe a few tens or hundreds of milliamps, and so there will be your current along the x-axis and your voltage up the y-axis. And if you put 0, 0 there, that voltage is going to go up to about 1.5 or 1.6 volts, depending on how fresh your battery is. Rs is a very small number, and so you'll expect, the negative sign means you'll expect to get a graph of negative slope. But if you have a scale that goes all the way up from 0, you'll find the slope of the graph is so shallow it will be very difficult to measure. And so this is a case where instead of going to the point 0, 0, we want to zoom out part of that scale, expand that bit of the graph out so that we can really see what's happening there. Now let's have a look at some typical data. Now here's some typical data from an experiment of voltage as a function of current for a small battery. And you can see if we wanted to choose for the X scale current, we can go quite happily all the way from about 0 all the way up to about 160 milliamps. So it would probably make sense to choose a scale for the current I, which has 1 centimetre corresponding to about 10 milliamps for our x-axis. And so 160 milliamps would be 16 centimetres along the x-axis on some graph paper. Now up the y-axis the voltage goes from 1.596 volts up to 1.618 volts. Do the subtraction, that's a range of 0.22 volts. Now if I plotted the graph in portrait mode on a piece of graph paper, I could probably do that because a piece of graph paper goes up 25 centimetres, and so making 0.001 of a volt on the vertical axis, the y-axis, might be appropriate. But I'm going to want to plot it in landscape mode. In landscape mode there's only about 18 centimetres up and down the vertical. 22 doesn't go into 18, so I'm going to choose a scale of 1 centimetre corresponding to 0.002 of a volt. And since I want a graph that starts at a reasonable level, I might start it at the level, the lower level, going from about 1.590 and work up from there. So let's do that. Let's get a piece of graph paper, and for the vertical axis, what I will draw is up the vertical axis. There will be our voltage up there. We'll start here at 1.590, and we go up in steps of 0.2 of a volt. So 2, 4, 6, 8, 10. That will be 1.600. 2, 4, 6, 8, 10. That will be 1.610. 2, 4, 6, 8, 10. 1.620. Along my along my horizontal axis, I'll find it convenient to just have 1 centimetre equivalent to 10 milliamps, and so we'll need to go out to about there, and we can start 0 there. So this is current I in milliamps. 1, 2, 3, 4, 5, so there will be 50 milliamps. 6, 7, 8, 9, 10, 100 milliamps. 2, 3, 4, 5, 150, and so on. So there I have voltage up there in volts. There's V on that axis in volts, units of volts, I on this axis in milliamps. And I can start now plotting some data. So when I equals 13.5, V is 1.618. So there's 10, 12, 13.5 is about there, and 1.618, 1.61, 12, 14, 16, 18. So 13 will be a point about there. That corresponds to my first point. Notice 16.2, 10, 12, 14, 16, 16.2 up there. That data point is also on 1.618. The resolution of our voltmeter is only 0.001 of a volt in this column. On this graph, 0.001 of a volt is half a centimetre. So we've got to go to a fair draw of current, about 19.7. There's 20, 19.7 will be just less than there. The voltage has dropped to 1.617, which will be there. Then 23.8, 1.616. 10, 20, 22, 23.8, 24 is about there. 1.616. Notice the voltage is dropping by half a centimetre at a time. It's a very coarse scale. Then 28.9 would be 0.61. And so gradually it's 614, 613 will be there. 1.611, and short of that, 160 there is there, 81596 is there. Now we need to draw some error bars on this data, and it's suggested that the uncertainty on each of the scales is plus or minus 3 digits on the current scale and plus or minus 2 digits on the voltage scale. Now 3 digits on the current scale means plus or minus 0.3. And on this scale here, that is 10 milliamps. 1 milliamp is about a millimetre. 0.3 of a milliamp is 0.3 of a millimetre. Is actually too small to plot. On the vertical scale, plus or minus 2 digits is plus or minus 0.002, which on the vertical scale is 1 centimetre. And so for each data point now, we can plot some error bars. They're basically plus or minus 1 centimetre. Plus or minus 1 centimetre. Plus or minus 1 centimetre. And finally, we need to draw a line of best fit. Which is probably about there. And to get some idea of variability in the slope, let's draw one line of worst fit that passes through all the error bars. And I'll make that my line of worst fit.